Hi everyone. Now that we've seen in section 7.5 how we use the Laplace transform to solve a differential equation, we're going to go back and keep looking at how we take the transforms of different types of functions. And the reason that we really need to be able to do that is because the first step towards using the Laplace transform to solve a differential equation is to take the Laplace transform. And so you need to be able to take the Laplace transform of all the parts of that equation, including what you have on the right-hand side, what we call, sometimes the non-homogeneity or the forcing function. We saw, not in any of the videos, but in lecture, back at the beginning of the chapter, a motivating example of why we wanted to use Laplace transforms. And in that example that you can go back and look in the book at, the forcing function was a discontinuous function because we were filling up, I think it was a tank at one rate, and then at some point we switched to filling it up at a different rate. And so it was the function on the right-hand side of the equation was defined piecewise. It was one way for t up to a certain point, and then after that, it had a different value. And if we used our normal methods, our sort of not chapter 7 methods of solving that equation, we would have to sort of break it up into different parts, and it would be very complicated. And what we find in this section, that Laplace transforms can be taken of functions with discontinuities in sort of an easy way, and it can remove some of the steps for solving equations with those discontinuous functions. This section is going to be a little bit heavy on notation, but most of the concepts in it are actually pretty straightforward. So it will just take a little bit of practice in the homework and such to get a handle on what the notations mean and relating that notation back to your intuitive concepts. So we're going to start off with a definition of what we're going to call a unit step function. So this is just a pretty simple function we're going to denote by u. U of t is defined to be 0 for t less than 0 and 1 for t greater than 0. Sometimes you'll see this referred to as a Heaviside function. After the person that sort of came up with, you probably wouldn't say that he invented the unit step function because that's a pretty obvious thing, but he invented the use of this for this whole set of theory. And I think the name Heaviside is kind of an interesting name, so I think it's worth saying and writing down when you get a chance. So anyway, what does this look like? Let's graph it. It's pretty obvious. We'll do our axes in black. We've got 1. And for negative numbers, we are over here. And for positive values of t, we're over there. The actual value at t equals 0, you could define one way or the other, but it really doesn't matter because we're going to be integrating things. And when you take an integral, a single point value doesn't really matter much. And so something that you can observe with this is that you could, if you wanted to, say, shift this to, sorry about that. If you wanted to shift that to some other number, like let's say 2, and you wanted the function to look like this instead, then you could use the same function, and now this would be just a transform, or translation of the unit step function. And then if you wanted to make it a little bit higher, say, so now let's go like this. There we go. So now let's say we wanted to shift it over 3 and make the height up at 5, well, we can still do that with a unit step function. We just have to sort of magnify it by a constant out in front, and then we'll translate it to -3, or t minus 3. So we can use this unit step function to sort of describe any single jump discontinuity that we might have. Okay, so now we have clean paper, and we've still got our unit function, or unit step function written on the side here. And so the unit step function, as we saw, it sort of has values on 1/2 of the axis. But what we really are interested in now is something that'll give us just like a kind of a pulse that will give us 1 for some period of time, and then we'll stop. And we could define this completely separately, but what we can also do is define it in terms of the unit step function that we already have. So here's a definition. And this is our rectangular window function. And we can also call this a square pulse or a boxcar function. That's another good name, I think. And here's where our notation gets a little bit hairy again. So we're going to call this capital pi. Yes, there's capital pi, from a to b of t. So this is a function that depends on 2 values, and then it's a function of t when those 2 values a and b are specified. And this is going to be defined as u of t minus a minus u of t minus b. And another way, or what this really ends up being equal to, is 0 for t less than a, 1 between a and b, and 0 for t bigger than b. All right, so why does this work? Why does this make sense? Let's draw a big axis over here. And first we'll do, in blue, our u of t minus a. So let's say a is right here and b is right here. And u of t minus a, like we saw on just before, is the unit function that's shifted over to a. So we're going to be like this. Okay, so this one is u of t minus a. Now in red, we'll do u of t minus b, which looks like this. Oops. So this red one is u of t minus b. And then in green, we will do the difference. So if we're to the left of a, we get blue minus red is 0. If we're between a and b, then blue minus red is 1 minus 0, so that's 1. And if we are bigger than b, then blue minus red is 1 minus 1, and we're back down to 0. So this is capital pi a comma b of t, okay? And so if we look at this with just, if we sort of come over here and just plot this without all the other functions, then we see we've got a to b. This is just a little sort of hats function. It looks like that. That's at a 1. And so this is going to come in useful for looking at just part of a function, which is why it's called a window function. So to see this, let's just get a brand new piece of paper. Let's say we have some function that looks like whatever it looks like. We'll draw it in blue. So this is some function f of t. And let's say we want to look at this at just what's happening between the values a and b. So we sort of want to erase everything that is not between a and b. So let's just sort of copy this over. Okay, so now let's say that we want to erase everything from a to b. So we're gonna do that with our eraser. There we go. We can make that bigger and erase the whole thing. And then erase all that. Okay, and how can we express this function? Well, this is just going to be, I wanted that in blue, f of t times our window function. Okay, so the window function just gives us a nice way of expressing some function, like a piece of a function. And why do we want to do that? Well, we can, let's see, express piecewise defined functions in terms of window functions. And that's going to make it easier to take the Laplace function of piecewise defined functions. So for example, let's say our function is f of t, and it's defined in a bunch of different ways. 3, so it's going to be 3 if t is less than 2, and it's going to be equal to 1 if t is between 2 and 5. It's say equal to t, whatever. I mean, I'm just I'm picking what's in the book, but this really could be anything. So if t is between 5 and 8, we'll define it that way, and then t squared over 10 for t greater than 8. Okay, so this is our function. And if we have taken Laplace transforms, we've seen examples of Laplace transforms of piecewise defined functions, and we actually computed it with the definition by breaking up the integral into all these different parts. And so now we're going to do it a little bit differently. We're not going to take the Laplace transform yet. I'm just going to write this in terms of window functions. So first, let me draw this function. First, there's my function f of t equals 3. And I have drawn this all the way across, but we really only care about it for values between 0 and 2. And I should have said before that this is really 0 less than t less than 2, just because for the Laplace transform, we don't care what's happening before t equals 0. All right, so that's the first part of our function. The next part is this one, the constant function 1. And again, we have sort of faded out all the parts that aren't between t equals 2 and t equals 5. And then the next part, we have the function f of t equals t that we only care about between t equals 5 and t equals 8. And then the last part is this parabola. And again, we only care about sort of what's happening on the right-hand side. And so by the reason that I drew the whole function in for each of these 4 parts is so that you can see that the bolded part or the not shaded part is sort of the same thing that you get if you multiplied the function by a rectangular window function. And so that's exactly how we can express our function f. Okay, so we can write f of t as equal to just first the red part, which is going to be 3 times a window function between 0 and 2 of t, plus, now the blue part, 1 times a window function between 2 and 5, plus t times the window function between 5 and 8. And then the last part is not a window function, but it's actually just a unit function shifted over. So that's the unit function shifted over to 8 times t squared over 10. So now because of the linearity property of the Laplace transform, we could take the Laplace transform of f by taking the Laplace transform of the sum of all these things. So now, really, if we knew how to take the Laplace transform of a unit function or a window function, then we'd be in pretty good shape. So that's what we're going to do next. Let's hit a new page, and we are going to find this. Let's say we want the Laplace transform of, let's say, an arbitrarily translated unit function. So that's going to be some function of s, and we'll just write down the definition. The integral from 0 to infinity, e to the negative st of u t minus a dt, which equals, this integrand is going to be 0 up until t equals a, so we can actually change this integral limit to an a, and then after that a, u of t minus a is just 1, so we get rid of that altogether. So now this is sort of reasonable. We can take this just normally, limit as n goes to infinity, of negative e to the negative st over s, evaluated between t equals a and t equals n, and we've done this one just a million times. So we get the limit as n goes to infinity of e to the negative s a over s minus e to the negative s n over s. And when we take this limit, this goes off to 0, and we just get e to the negative s a over s. So what is the result that we've just found here? Let's sort of rewrite it. We'll stick that over here. So the key result, we have the Laplace transform of our unit step function is e to the negative sa over s. Another result we can get from this is just go backwards. We can get an inverse Laplace transform of e to the negative sa over s of t is the unit step function, t minus a. And so if we have anything where we need to go backwards from an exponential function, we have a way to do that. And then let's do one more. We really, as we saw in our last example of the piecewise defined function, we really want to be able to take the Laplace transform of the rectangular window function, but that's okay because we can write that in terms of a sum of unit step functions. So if we want to take the Laplace transform of our window function, a to b, it's a function of t, and then the Laplace transform is a function of s. This is just the Laplace transform of u of t minus a, and we can use linearity of Laplace transform to write this to break this up. Oops. All right, write that the right way. And this is equal to the difference e to the negative SA minus e to the negative SB all over S. Okay, now we're going to do one last thing. And that's a theorem that talks about what the Laplace transform of a function multiplied by a unit step function is going to look like. So let's let big F be the Laplace transform of little f. We'll say this exists for S bigger than A, some positive A. So if A is a positive constant, then we get two results. One, we can write this in another color for fun, the Laplace transform of F translated times the unit step function is going to be, so if we do translating things and cutting them off in the t universe, then that equals exponential. That's the same thing as multiplication by an exponential in the f universe. And conversely, the inverse Laplace transform of e to the negative as f of s, which is now a function of t, is equal to the translation. So now the f of t minus a is a little bit weird because we've always been dealing with f of t. And the reason for that is just that it's going to make our computations a little bit easier. And then we will see at the end sort of how we deal with this in practice. So let's prove this. So we are interested in the Laplace transform of f of t minus a times u of t minus a. And so we can write out the definition. It's always a good place to start. E to the negative STF, t minus a, u, t minus a, dt. Now, what's happening with what's happening with this integrand here? So when we do f of t minus a, we are, let's kind of just come over here and draw this. We are shifting things. So first we start off with maybe some f that looks like this. So this is f of t. And then if we shift it over to a, now our shifted one might look like this, f of t minus a. And if we now multiply that by the u of t minus a, we're going to erase everything that came before it. So our function is going to kind of look like this. And so this green one is, f of t minus a times u of t minus a. And so the important part for the integral that we're doing is that our green function now, the f times the u is equal to 0 for everything less than a. So let's come back over here and we can keep going. So this is going to be equal to the integral from a to infinity. And from to the right of a, the u is just 1, and so we've got e to the negative st times f of t minus a dt. Okay, now to do this integral, what we want to turn this into, remember what we're trying to show. We're trying to relate this integral here to the Laplace transform of the original f. So we want to try to get this back looking just like f. And we'll get rid of that. So if we can do we're not going to do a u substitution because we already have a u, so I'm going to do a v substitution. And I'm going to let v equals t minus a, and then dv is just going to equal dt. So now I can write this as the integral. Let's leave my limits for a second, and I'll still have e to the negative s v plus a, right? Because t, from here, we get t equals v plus a times f of v dv. And then what are my limits going to be if first we started off from t equals a, and then that would, if we plug that in for t into v, we get 0, and then infinity will stay the same. So let's do those in black. 0 to infinity. Hey, that's kind of perfect. That's just what we wanted. Now one of these exponential terms can come out if we break this up into e to the negative sv plus a equals e to the negative sa times e to the negative sv, right? And so the one that doesn't have a v in it can come outside the integral, e to the negative sa. You know what? Let's write that as e to the negative as so that it looks like what we have in the statement of the theorem. Integral from 0 to infinity, e to the negative sv f of v dv. This is exactly the definition of the Laplace transform of little f. There we go. So now we can rewrite this like e to the negative as big F of s, and that's exactly what we wanted. I'm not going to do the second part because it's just sort of obvious from the definition of inverse. Okay, so now the very last thing is we're going to write down a corollary where we want to take our previous result, which, hold on a second. Poof. Okay, so we've got our result over here, which I'll just box up. But let's say that we want to compute the Laplace function of just any sort of like an f of t times some shifted unit step function. So in that case, we will sort of let g of t equal f of t minus a. So now g is the shifted version of our original function. And so then we get that f of t equals g of t plus a, right? That's just kind of a simple substitution. Okay, so then our previous result, that guy here becomes, change to blue, the Laplace transform of g of t times u of t minus a equal e to the negative as times the Laplace transform of, so what we had here was big F of s, which is the Laplace transform of regular f, which is g of t plus a. And so here is sort of the nice handy-dandy result. Now, I'm not going to do any examples in this video. I can do some examples when we meet in class about this lecture on Thursday, but I would suggest that you read through some of the examples in the text and then practice it in the homework and ask any questions that you have about it. All right, that's it. Thanks.